Hi, everyone. My name is Javiera Guedes, and I'm a data scientist at Teralytics. Formerly, I was a computational astrophysicist, and if I have time at the end, I will show you a little bit about how simulations of the universe work, but let's see if we get there. The topic of today's talk is the origin-destination matrix using mobile network data. And I'll explain in a second what that means. But before I do that, I wanted to introduce you to Teralytics. So Teralytics is a startup, and even though it's a startup, we are already a global company. So we have offices in New York, Zurich, and Singapore. And what we do is we transform raw telecommunication data into useful insights about human mobility behavior. We process billions, hundreds of billions of events every day in near real time, covering location, telecommunication, data carries location, of course, as well as spending, finance, and other data sources. Like I said, from the telecommunication companies, mobile data consists of location data. We use powerful analytics in order to process this massive amounts of data and aggregate it into useful insights that are later shown into nice dashboards that allow the customers to slice and dice the data and try to understand the insights that they need for their business. We care a lot about privacy, so all the data is, of course, de-identified. User IDs are hashed, not only hashed, but rehashed over periods of time. The data is always extrapolated and k-anonymized. So a lot of worry here about privacy. And let me tell you a little bit about the problem of today. So I said that we're going to study a little bit the problem of the origin-destination matrix. We call it ODE matrix. And basically, what this means is that in transportation processes, we want to understand how people move from point A to point B, from origin to destination. And in the old days, of course, this is very relevant, for example, for transportation companies who want to understand how many buses they should have or how many trains. What happens in the case of breakdown in the train system? What are the alternative routes for people? These kind of things are very important. And so we want to try to understand that. So before us, one approach to doing this is statically. So basically, you have a matrix T, a matrix T with elements Tij, and the number of trips, which is each element of the matrix, will consist of the number of trips from I to j, or from I in general times the fraction of the trips attracted to j. So basically, in this way, you can, using census data or survey data, try to understand how people flow from region to region. And of course, this will give you an average over a certain amount of time, whatever the course of the census was, of the survey. And this data is, of course, not dynamic. But when you have telecommunication data, this data is intrinsically dynamic. And you can do this as a function of time, in whatever time bucketing you want. You can do it every day, and you can see trends in the data. So how many people are going from I to j every minute of the day, right? The particular case that I will talk about today was done in Germany. The point is to try to understand how people move through Germany. The matrix we try to calculate is actually a very simple table, right? So we have regions 1, 2, 3, which are the destination regions, regions 1, 2, 3, which are the origin regions. And the goal is to fill every element of the matrix here. The regions are actually, if we visualize them, they look like this in Germany. This is zip code level 5 geometries. And, but we're trying to actually calculate more than just one matrix. We do one matrix per time bucket, so every 15 minutes or 1 hour, or whatever the customer needs are. We do one matrix per mode of transportation, because we also want to try to understand how people move through these regions. We have what mode of transportation. And also we do 2 different matrices for departure and arrival time. So for this particular project, we wanted to do this over 40 days. And for this, we used about 100 billion events, telecommunication data events. So I will talk a little bit about the approach that we use to compute this matrix. Everything on the pink zone here is done with Scala Spark. But certain things cannot be done like that. So basically, we have the data stored in HDFS. We have some additional information that we merge with the telecommunication data. For example, the location of the cell phone towers. And then we process this raw data. We do some filtering. We do a group by subscriber. We do what we call location estimation. So we go from the cell phone tower location to where we think the user is, or the trip takes the user. And then we do what we call MOT detection, mode of transport detection on the strip. In some cases, we do routing. And finally, we do trip aggregation and k-anonymization. I will explain a little bit later what k-anonymization means, but this is part of our data privacy. So just to give you an example, let's say that a trip begins at an origin here in Brooklyn and ends here at a destination in Long Island. And as the person goes through the different parts of the city, it will generate events in different cell phone towers along the way. So this is shown like this. So basically, we don't know exactly how the trip happens, but we know that several cell phone towers were triggered at different points during the day. So cell phone towers are associated with what we call a coverage area, which in some cases can be extremely large, right? So this is New York City. The more dense the city is, the smaller sometimes the coverage areas, but these events are generated at towers that have a coverage area that looks like this, right? So, and these events have usually a timestamp associated with them. So basically, the trip begins here at 8 a.m., continues here, then an event is generated even in this tower, and ends here at the destination around 10 p.m. Okay? So, and all of these cell phone towers have this very extended coverage areas. So part of our job is to actually try to understand, to reduce the uncertainty from these large coverage areas to smaller regions of uncertainty that would allow us to understand the path that this mobile device took along the way the trip was constructed. And so this is what we call location estimation. We do this using various statistical methods, including camel filters and so forth. So once we have the estimate of the location, one thing we can do is try to figure out different routes for the trip in which the trip could have happened. And these are all possible routes for this fictitious trip. And so we don't really know, exactly how the trip was performed, but we believe that, for example, this is the most probable scenario for this particular trip. And we can even go further and try to, for this most probable trip, try to understand what mode of transportation was dominant within the strip. We are not concerned about individuals or individual trips. All of this data is going to be aggregated in the end. And so what we care about is really how many trips happen from point O to point D. How many people, or how many trips occur between these 2 points. At the end of the day, this is what we care about. Some telecommunication companies are not able to provide, actually, the coverage estimation for their cell phone tower locations, but we can estimate that. We can use our location estimation algorithms, actually, to do expectation maximization around the cell locations and try to understand approximately what the coverage area for the cell phone towers is. And this coverage estimation looks a little bit like this in New York City. Once we're done with the location estimation, we can actually basically stop there for a minute and do some aggregation. And when you do that, the map looks like this. So this is New York City again. Darker areas represent points or areas where most strip crossed. And this can be done in any desired geometry. So you can aggregate by street, by zip code, by state, by whatever you want. In this case, we decided to aggregate by hexagons, because hexagons have the advantage that they're easily nestable, or not so easily nestable, but they're nestable. They're space filling. They provide a good sampling of the underlying geometry, much better than squares, for example. And it allows us to do fast data visualization and analysis on top of the segregated data. Just to give you an example, also, the reason we use hexagons, as I said, is that we can nest them and we can zoom in and out. We can use them for our visualizations. And for example, if we zoom out, we want to see the data in a larger hexagon. And we zoom in, we want higher resolution. We can go to a small hexagon and see how much flow there is through this hexagon, or how much time people are spending in these areas, and we can slice and dice the data the way we want. So this is something very nice about this aggregation and visualization that we do as part of our data processing. I mentioned that we also try to understand how the trips, what the dominant mode of transportation for one particular trip is. And one thing we want to understand is whether it's a flight, whether it's a bus trip or a train trip or a car trip, or whether we actually don't know what kind of trip it is. So for this, we do what we call mode of transport detection. For example, when we're trying to look for flights, we look at airports and we look at events generated at airports. We do what we call stationary detection, and we make sure that there are stationary points at the airports. Sometimes during flights, events can be generated. So we have to look at features like the origin and destination airports, whether there are stationary points there, whether there's airport nearby, whether the speed of the flight is consistent with flight speeds in general, so we have speed constraints. And obviously, we have to work only on top of feasible routes. I mean, if you are next to Tegel Airport the whole day, that may qualify you because you are in a stationary point around there, but you're not going to go from Tegel to Tegel, so that's not a feasible flight. Moreover, we want to classify trips into train or car trips. So at the moment, we use very simple features. For example, the feature derives from the distance of these events to railways or highways, and we create probabilities based on that. If the probability of car over train is greater than a certain threshold, then we associate this trip with a car trip. Else, we do it with a train trip. And if we are not sure, we either use routing, for example, OTP routing, or we just say, well, we don't know. It's an unknown mode of transportation. And after we do all this, we come up with a final product. And it looks something like this. So we have what we call the OD matrix product, which is not really a matrix, but it's a data cube, where we have departure time from the origin, arrival time at destination, mode of transportation. Everything is aggregated by whatever region of interest the customer has. This can be a state, zip code, or anything. And it's bucketed in time, 15 minutes, an hour, a day, a week. And in our dashboards, we can dice and slice this data in a way that is useful. For example, here we have, for one particular week, we can click on each of the bars and actually see the matrix changing over time, as well as the mode of transportation. We can see how many more trains there are operating, for example, during the weekdays versus the weekend, how many trips there are as a function of time and mode of transportation. We can see trends over the course of the day and other features as well. So we present the data in this way. It's very nice. Also, you can filter by the flow. So basically, how many trips there are from origin to destination. And as I said, we did this. So this is an example where we just took a few areas in Frankfurt and in Berlin, and we computed this matrix like this. So for example, every line here represents a number of trips. Thin lines represent very few trips, but very thick lines are already thousands and thousands of trips. And then we have to do this for the whole Germany. So as I said before, we have to compute this for several matrices over the course of 40 days, taking into account 100 billion events. And there's one step that you have to apply, obviously, before you create a complete matrix, and that is extrapolation. The data has to be extrapolated because nobody is interested really in how many trips there are from Munich to Hamburg, according to our telecommunication company that we work with in Germany. But we want to understand how many trips in total, extrapolated to the total population there are. And in order to do this, we use a kind of gravity model, so basically based on the local market share in different regions in Germany, accompanied also by the population in these different regions. And we can compute a map like this. This is a map of market share for this particular telecommunication company partner that we have. And using this very simple extrapolation model, we can apply this to our matrix and compute final counts. The final result looks a little bit like this. This is the matrix for the entire country. Again, same dashboard. You can slice it by day of the week. You can slice it by mode of transportation, time of day. And here, k-anonymization has already been taken into account. And k-anonymization, what it means is that if we have between two regions, the number of trips being less than k, k could be 5 or 10, or then this data is not shown. So basically, we protect the privacy of the individuals by removing the data that has very low numbers. So the data is usually accompanied by these nice visualizations, and so there's one more step that needs to be done to convince people that we are actually doing a good job here. And this is probably the most difficult thing to do, because it's impossible for us to go in every train or in every highway and count the number of trips happening between these regions, right? So, but there's ways in which we can validate this data. One way we can validate the MOT classifier, for example, is to use very limited calibration data that is labeled in order to calculate the precision and recall for this particular classifiers. So for flights, we achieve a precision of 0.96, so these precisions are usually very high for all these different modes of transportation, and the recall is usually much lower. And the reason is that our classifier is always more likely to classify something as unknown because it's very conservative than to classify one category into another. Other things we can do to validate our data is to look at limited ground truths that we have from our partners. And, for example, see actually how many train trips or car trips there are in comparison to data provided by them, by our customers. And we can also do common sense checks. So we can look, for example, whether two elements of the matrix that are symmetric are actually symmetric. So basically, whether car trips between Berlin and Frankfurt are similar to the number of car trips between Frankfurt and Berlin, aggregated over the course of a week. For example, these numbers should be roughly balanced, and we do these checks. And another thing that's very important for Germans, at least, is the Bundesliga. So one thing we absolutely must check is whether we see whether we see this truly dynamic elements of our data playing a role here. So can we see people coming from all over Germany to come and see a football game? We do actually see this. So we took some data for the location where the Allianz Arena is, in Bayern, for Bayern Munich's stadium. And we can look at that over time. So we can look at how many people are coming to the stadium from all over Germany over time. We're looking at one particular region. This region contains highways, so of course, there will always be some activity. But on the day of the game, September 15th, 2005, we see a strong peak for this particular day, and that is very indicative of course, that we are actually seeing these people coming. This also can serve as an extrapolation mechanism because we know actually that the stadium was full that day. There were 75,000 people there. And so we can do this for all football games in the Bundesliga retrospectively and see the same peak happen over and over again. And so that's a very nice also validation of these results. I mentioned we are a global company, so we don't only have offices in different parts of the world. We also have data, telecommunication data from different parts of the world, which is extremely nice because, for example, if I want to open a new coffee shop in a country that I know nothing about, I want to see how people flow through the city, how people flow through the streets of that city. And these are things that I didn't talk about today, but we also do as well. And I want to know where to put my coffee shop in that city. Where is the best place with the best flow at peak hours, for example? Or if I want to open a new restaurant in China, I want to know where people go for lunch every day. And so we can do this in regions, not only in countries. So we can do, for example, an OD matrix only within Berlin. And this is what it looks like. We can do this in certain regions in China. And this is what it looks like. We can do it in the US as well. And it's important also that to do it in smaller countries, like Singapore, for example, because there we have seen major failures in the transportation system happening that are very harmful for the people. So basically, we had a talk before where people are trying to understand when a failure happens in the train system. What we do is we want to try to understand that when that happens, how people are going to get home. So what are alternative routes to go from point A to point B if one route fails? So it's important for us to have data on all these different parts of the world and to do this work everywhere. I told you I would mention something about the universe. perhaps at the end of the talk, and this is it. So why we use Spark in our processing pipeline? Obviously, because we have terabyte data sets of data we have that are not manageable in a single CPU. We have parallelized computing. So we want to store, so Spark works, is very compatible with technologies that we use, like HDFS and Accumulo as well. And obviously, the strips are independent from each other, so the data is extremely easy to parallelize. This is not the case in other fields. This is not the case in astrophysics. Because in astrophysics, when we try to simulate a portion of the universe shown here, there's actually dark matter. Each dark matter particle is basically collapsing due to the gravity from every other particle in the simulation box, and this is very bad for parallelization. Also, the domain is extremely inhomogeneous. So, but at Teralytx, our life is much easier because strips are independent. So that's one very nice thing. So Spark is also used for slicing and dicing the data in the dashboards, but we don't use it for visualization because in this case we have to query very small amounts of data. The data at this point has been already aggregated. And so if you want to learn more about our company or what we do, our different projects, feel free to go to our website, teralytics.net. We are based in Zurich, Switzerland, and of course, if you're interested in working with us, feel free to go there and join us. Thank you very much.
Any questions? Okay. Thanks for the talk. So, when you see a customer or a single person moving, obviously you don't know where is she exactly. How do you compute where is she? Do you use a best server estimation for the turret where she is, and you only use a single turret, or do you use a probability distribution for all the turrets, and then do aggregations for the whole community?
That's a very good question. In some cases, some use cases, we have done exactly that. So we have taken a more probabilistic approach, and we have aggregated the different probabilities for one particular trip. For example, when we look at street flow, we have to do this because it's impossible for us to determine exactly the geometry of the trip in the city, right? But when we do something like OD matrix, we don't need to do this because we only care about origin, destination, and most likely mode of transportation along the way.
Thank you.
Mm-hmm.
Any more questions? Yes. I recognize that face.
Thank you for the nice talk. I have a question. What's the positional accuracy of people after the triangulations, typically?
Also a very good question, and this is not, I cannot give you a single number because of the nature of the coverage areas and the nature of our algorithm that is also probabilistic. We have a statistical confidence area of the position of a trip at a particular point in time. And this can be anywhere from 5 meter squares to 500 kilometers square. So it's, there is a large uncertainty in a particular point in time. Because we have information of previous parts of the trips, you can imagine a Kalman filter style approach, then the uncertainty can be reduced for the entire trip, but it's never accurate to the meter square.
Okay. So let me ask again, what would be the accuracy per within big cities, and at what frequency do you collect this data from the users? I mean, from the mobile users, I assume.
In big cities, I think, I don't want to give a precise number because this varies a lot from trip to trip and from coverage area to coverage area. But I would say within between 100 and 200 meter squares. This is actually the size of these hexagons that you see at the lowest resolution level. And the other question was how often we get this data from the telecommunication companies.
I mean, at what time interval they collect this data from the user?
This data is, actually we don't collect it, so the data is always in the data centers of the particular telco companies. But this varies from company to company, from minutes to days.
Thank you.
Okay, thank you. One more question, I think this time.
Cool, thanks. Geospatial applications of big data are always fascinating. Can you speak a bit about the tools you use, be it for routing, for mapping, and for visualization?
I was specifically very broad on brushing out these algorithms because obviously I cannot give away certain things that we do. What I will tell you is that obviously we do use Kalman filtering in one way or another. We do use OTP routing in some cases, so we route using OTP. OTP gives you a probability for different modes of transportation as well, so we're not sure. Of our own classifier, we go and ask OTP what OTP thinks that the mode of transportation is. Yeah.
Cool.
Hi, it was so interesting. Not from the technical or analytical point of view, I have a lot of concern about data privacy right now, because this is a monstrous Big Brother system.
This is a what?
A huge Big Brother system. So basically, I was surprised because of Germany, because Germany actually is asking, there are some operators which are providing, making use of private use of data, of mobility data, where you can opt out. But there are certain rules. So the basic rule of taking anonymization of the cluster level of 5, this is mandatory by law. The question will be, do you put some limits on your analytics when you're working?
We put a lot of limits in our analytics when we're working. So basically, I mean, there's many things, right? So first of all, we don't know nothing about individual people. We absolutely know nothing. The rehashing that I was talking about happens in the course of a day, for example, in some telecommunication companies. So even if I wanted to, as an employee of Teralytics, to know, to try to track somebody, I couldn't because of this constant rehashing of identifications, right? The data is aggregated, so in the end what we deal with is large numbers of trips, and we're not concerned with individuals. So we're not concerned with individual trips or so. We just care about aggregated data, we care about flow through cities, and we care about understanding behavior in the larger scale.
Okay, thank you very much. Please show your appreciation. Thank you.